The Autonomous Operating System, the AOS, model-based plug-and-play autonomy for robots in partially observable probabilistic domains with noisy sensing, a research of Or Wertheim and Dan Suissa under the supervision of Professor Ronen Brafman. Motivation. An increasingly wide range of robot skills is currently available. How can an autonomous robot use them to perform tasks? The current state of the art is to use handwritten scripts or state machines to schedule skills into effective behaviors. The challenge is that scripts or state machines are non-optimal, hard to maintain upon environment change or robot skill upgrade. The solution is to use AI planning algorithms to control the robot. The problem is it requires AI expert and a significant integration effort. Our goal is to provide plug-and-play task-level autonomy for robotics. Our solution, the Autonomous Operating System, the AOS, which offers several advantages. Conceptually, we provide full POMDP support with stochastic actions, partial informations, noisy sensing, complex goal, and optimized behavior while balancing trade-offs. We offer an abstraction mapping, which is an explicit and principal mapping between the skill model and skill code. We use generative POMDP models that are based on probabilistic programming language constructs. It offers greater expressive power, easier to specify, and enables much faster sampling rates. Generically, we provide a true plug-and-play system. Given properly documented skill code, no additional programming effort is needed. Documented skills can be added incrementally and used by the system. The AOS uses reinforcement learning to auto-generate MDP heuristics of POMDP solvers. The system has a GUI to visualize the robot belief state distribution and understand the robot's behavior. So how do we use the AOS to develop an autonomous robot? The first step is implementing basic robot skills like navigation, object detection, or arm manipulation. These are out of the system's scope. The next step is documenting the skills and environment. An environment file is used to specify the skill-independent aspects of the model. These include state variables, terminal states, initial belief, and state-dependent rewards. Each skill is documented using an SD and an AM file. Semantically, the SD specifies a fragment of a POMDP associated with a specific skill. It describes the expected high-level impact of applying the skill, how state variable values change, the associated reward or cost of the skill, and the information the skill will supply. In POMDPs, these are called the transition, reward, and observation models. The AM file connects the more abstract model of the skill with the skill code. It specifies how to activate the skill code and how to translate skill code execution, including code return value and public information, such as ROS topics, to an observation corresponding to the model. We will now overview a part of an experiment involving a simulated armadillo robot, a mobile base with an arm, to test the POMDP model advantages given partial observability, noisy sensing, and stochastic effects. The simulated environment included a room with two tables, each with a can on it, and a corridor with a person. One can is very difficult to pick. Its true height is 10% of what the robot perceives. The robot starts near the table with the difficult can. Its goal is to give the can to a person. We implemented 3 skills: pick can, navigate to a person or a table, and serve can to a person. We used 2 versions of the pick SD, a rough model that assumes the probability of successful pick is independent of the selected table, and a finer model in which success probability is conditioned on the robot's position. First, we experimented with each skill and used the observed statistic to write the SD file. Then we specified the AM files and the task. This information suffices for the AOS to control the robot throughout the task. We observed that pick returned success if motion planning and motion execution succeeded, which did not imply that the can was successfully picked. Therefore, we enhanced our pick AM to listen to ROS topics published by the arm driver, like gripper pressure and joint angles, significantly improving the observation model accuracy and the resulting policy. To conclude, we will see how the AOS solves the toy collection domain, which is a full POMDP. A robot receives a reward for bringing toys to a child. The toys' locations and values are unknown to the robot, yet some prior knowledge is given for the initial belief. The robot has a navigation skill that may fail and has a noisy report for its success. The pick skill can only be used 6 times, and it only works if the robot is near the exact toy it tries to pick, yet it receives an accurate observation of the pick's success. This example emphasizes the advantage of using POMDPs. See how actions are selected based on the belief state distribution rather than a single possible state. When the belief state is visualized, we can see the reason in the robot action selection. See how applying probabilistic actions like navigation adds uncertainty and how observations focus the belief based on their accuracy. The failed or successful peak observations supply valuable information that reduces uncertainty and assists in decision making.